Good morning. First of all, I would like to thank the Societat Catalana de Nanotecnologia for giving me the chance to be here today talking about graphene nano-antennas for wireless communications at the chip scale. I'm Sergi Abadal from the Universitat Politècnica de Catalunya and very happy to be here today. Processors lie at the heart of all our devices and also in the cloud. So that's the reason why we find them in cell phones, in laptops, in data centers, in drones, appliances, or even in the connected car. And the thing is that we want them to be faster. We want them to be more efficient so that the battery does not run out very quickly. And we want them fast and efficient for everything, from mundane tasks such as social media to scientific computing or AI processing and so on and so forth. There are two ways to architect computing systems. First of all, you have CPUs. They are general purpose processors, which are relatively good at all tasks. The recent trends are going to a multi-core kind of design in which you have multiple processor cores within a single chip. And these processor cores are interconnected to share data and to synchronize. And also the trend is to put more and more and more processors every day in a single chip or in a few chips within the same computing package, which leads to, in theory, higher performance, but also increases the importance of this communication to move data, synchronize and share data, to the point that communication becomes even more important than computation at some instances. On the other hand, we have specialized processors, which are amazing, but only at a few tasks, and they are terrible at any other task. In this example here, an accelerator would be very good for AI, but very poor for any other task. This is a trend that is thriving in computer architecture nowadays, especially in the field of AI, with many new designs of many new accelerators, many new processors, which are accelerating a given type of application with very complex architecture. But more importantly for us is that these are extremely data hungry, so that communication becomes crucial. In the middle, a new trend emerges in heterogeneous systems, in which the aim is to pick and place a few CPUs and a few accelerators that are good at different things, so that the resulting system is very good at AI, very good at graphics, very good at few things, and relatively good at everything else. But there's a problem. Communication is important in CPUs and it's important in accelerators. So in heterogeneous systems, they are not different, right? Moving data across the different elements of a heterogeneous system, it's going to be a key determinant of performance. Yet, this is very challenging because of the massive speeds that accelerators require, because these are system dependent, depending on the mixture of accelerators and CPUs that you provide. They are uneven spatially and dynamic temporally. So communication becomes different phases of computation lead to different communications from one point to many others, from one point to another very specific point, and these things change over time. Right now, the main way of interconnecting these computing systems, both homogeneous, heterogeneous CPUs and accelerators, it's through wired interconnects. So chips have multiple metallization layers with which we implement the different interconnects of the system. So these interconnects essentially connect the different components of a chip of different chips, and essentially this is the way how to carry the data that needs to be moved within an architecture. An example here of a big processor that we can find nowadays is a Samsung processor that we can find at the heart of a Tesla car, with many different elements routed through the same chip, and then on the top right, we have kind of a artistic imagination of how the different metallization layers are routed through the chip so that we can interconnect all the different elements of the processor. This system leads to very high performance because the wires are placed exactly for the needs of the processor. But on the other hand, there's very low generalization because if the processor changes a little bit, we need to redesign the whole processor with all the cost that this incurs. And also, there's also a high cost because of over-provisioning. We need to predict which is going to be the communication loads from where to where in different points in time for different applications that this processor might be running. And then we need to take the worst case and design a wired interconnect to cover all these different cases. This is called over-provisioning and leads to many more wires than would be strictly necessary if we didn't have to over-provision. The main issue of wired interconnects is its rigidity, right? Wired interconnects are laid down. There needs to be a physical infrastructure between transmitter and receiver. So the problem is that this is rigid and cannot be changed over time. And that's why we need to be provisioned, because since we cannot change it over time, we need to cover all the cases beforehand. So that means if we need to introduce a new piece of memory, a new application that changes the whole perspective of the different communication patterns, then we cannot rewire the processor. We cannot adapt to those changes in the communication. So that's one of the reasons for bad generalization and poor cost scalability of wired interconnects. So, reach this point, we have accelerators, we have CPUs, we put them all together in heterogeneous systems, and wired interconnects are fine, but they are not the best. So there's a problem with interconnects. So to avoid slowing down processors and the computation, we are in the need for fast and versatile interconnects beyond what wired interconnects can offer. So this is where we arrive to our proposed vision. We propose to integrate tens of miniaturized antennas into the chip of a computing system, so that the communication is going to be wireless through the processor package, and also this communication is going to be programmable. Right? We are not aiming to replace wires. Wires are very good at what they do, but we can, with wireless communications, we can complement wires, because we have inherent broadcast capabilities, we have this versatility, and also we have low latency, which is very important for communication on chip. Right? So this is our proposed vision, in which we have antennas on different chips of the system, and also these antennas are tunable so that we can change the frequency resonance of these antennas, so that we can implement multiple communication channels. And also we envisage that these antennas will be able to direct the electrical field to different parts of the package, so as to implement multiple spatial channels of communication. Of course, this is hard to do with current antennas, and that's why I'm here today, to talk about how we can do this with graphene antennas. So if this vision is achieved, we would still have high performance, because we're going to be even better than a system that has wires, because we are adding a wireless layer on top. We would have excellent generalization, because wireless can adapt to the different needs of an architecture while they change, with a moderate increase of cost. Antennas should not be extremely expensive to integrate into the chips of a system, since this is already on-chip antennas are already relative for other types of systems. So one of the main reasons why we think that wireless can provide all these fantastic properties is because of its flexibility. So now, if you want to add a new memory chiplet or a new memory chip within the system, or the needs of the system change because a new application has come, then wireless communication can adapt to those new elements and these new communication patterns by changing the frequency channels, the spatial channels, and also sharing the different other channels through the different antennas without having to rewire anything. So what is the main impediment for not implementing this already? The antennas, right? One of the first problems is that when you try to integrate an antenna on chip, it's the size, right? The size of a resonant antenna scales inversely proportional to the length of that antenna. So if we want to have very small antennas, we need to go very high in frequency. And generally, this relation is quite known. So if we need to go to hundreds of micrometers, tens of micrometers, which would be very nice for the on-chip scenario, we cannot with metallic antennas, because that would be going to the optical regime, which means not having transceiver circuits and the circuitry necessary to establish the communication, and also having problems of path loss, distance dependent path loss within the chip. Even more, metallic antennas, they are not tunable inherently. They are not tunable per se. So you need to add things around the antenna if you want to make them tunable. And if we want to make different spatial channels, you want to control how the antenna is radiating around itself, right? You need to use antenna arrays, which means putting more antennas side by side. And if one antenna is already large, then an antenna array is not affordable. So we need a new element that is going to be able to execute that vision of spatial frequency channels using antennas that are tunable and that allow us to create these spatial channels. And we envisage to do that with graphene, right? That's what led us to today. We think that graphene antennas are the key to agile interconnects for modern computing systems. And I'm going to explain you why in the next half of the presentation. I don't think I'm unveiling any secret when we talk about graphene, and this one atom thick honeycomb lattice of carbon atoms, theorized in the 40s and discovered first isolated in the early 2000s by Gaiman and Novoselov, who were awarded the Nobel Prize. I'm pretty sure that you already know this, and you already know that graphene has outstanding properties due to its strength, flexibility, electrical conductivity, and so on and so forth. But let me focus on what's important for us today. Besides the applications, the many applications that the graphene flagship is unveiling, what is important for us today is that graphene has excellent conditions for the propagation of surface plasmon polaritons in the terahertz band. Right? Surface plasmon polaritons are electromagnetic waves guided along a metal dielectric interface, which are blah, blah, blah. But what's important for us is that they are slow waves. So with this intuition that they're going to change the special relation in the material, and they were going to change the relationship between frequency of resonance of an antenna and their dimensions. And actually, that's what makes them unique, that this happens in the terahertz band, and not only this, but also that plasmons are tunable, so that we, I'm spoiling my presentation, but we will be able to tune the antenna at different frequencies. So exactly, we come back to this slide in which the scaling an antenna is difficult for us, because if we want to go to the length that are going to be affordable for us in the multi-core processing systems, then we're going to radiate in frequencies that are too high for wireless communications. But it was theoretically demonstrated in around a decade ago through theoretical modeling of the spatial relationship and the spatial relation and modeling of the antenna, that antennas using graphene could be resonating 1 or 2 orders of magnitude lower in frequency than their metallic counterparts, meaning that we could reach around 1 terahertz of resonance while having antennas of a few tens of micrometers, which is again 1 order or 2 orders of magnitude smaller than the length that you would need for a metallic antenna to radiate in the terahertz. So that's very good for us, because it allows us to for a higher integration of graphene antennas, and this opens the door also to antenna arrays and other things that would generally consume too much of it. So what we did is to take this theory and try to simulate it to confirm that actually this is actually what would be happening. So we modeled a very simple graphene dipole with a photoconductive source in the gap between the 2 dipole arms over a conventional substrate, and with biasing lines on the sides to provide DC biasing to the graphene arms. So we evaluated the resonance of the target antenna changing the dipole dimensions, and in this case, what we need to look at is a place in which the real impedance is high and the imaginary impedance crosses 0 or is very close to 0. And doing that for gold antennas and for graphene antennas of the same sizes, we obtain 1 order of magnitude decrease, or close to 1 order of magnitude decrease, especially when the antennas are in the lower side in terms of size. So when the graphene dipole is around 10 micrometers, then the compressibility of the antenna, let's say, was 1 order of magnitude, which was impressive. So we also, with the same setup, same simulations, we just changed the Fermi energy, the amount of voltage in the end that would be applied in the DC biasing, without changing the size of the antenna. So we see that this biasing is changing the electrical size of the antenna. In a sense, it's changing the frequency of resonance. So if we're not changing the physical dimensions, and by changing the voltage, we are changing the resonance frequency, then we are tuning the antenna. So we see that there's a pretty wide tunability in these antennas, which is not easy to obtain in regular conventional metallic antennas. So we see a resonance from 1.5 to almost 3 terahertz. So double the frequency by changing the chemical potential, the Fermi energy, by a wide margin. And it also changes the efficiency. So in the end, there's a trade-off. We observe that there's a trade-off between miniaturization and efficiency, because antennas are more efficient when they have a higher Fermi energy, where they are less miniaturized. But also that allowed us to think, right? So tunability does not exactly only mean that you can change the resonance frequency, but if your device is trying to transmit at a given frequency and then you tune it to another frequency, you're essentially tuning it out. So you're removing the antenna from the picture, let's say the electromagnetic picture. So we thought, why not try to exploit that property to try to make up for the loss of efficiency or try to provide even more flexibility, even more versatility to these antennas. So that's what Graphene is offering. And we approach different designs. First of all, we tried a Graphene antenna and simulated this Graphene antenna with a dielectric resonant antenna on top, in which the thickness of this dielectric on top of the Graphene antenna is also, depending on the frequency at which you design this for, this top dielectric is also resonating. So the idea is that depending on the Fermi energy that you provide to the antenna, is actually the Graphene antenna that is going to resonate and radiate. And depending on the Fermi energy, you're changing the coupling of the signal to the dielectric resonant antenna to the point that at a different Fermi energy, you would be able to resonate through the dielectric resonant antenna to provide a higher gain, which would be provide a gain higher than only the graphene dipole. And this is shown in these pictures here, in which type 1 is the graphene dipole resonating, type 2 and type 3 are hybrid, and the DRA resonating respectively. So you see that the type 2 and type 3 have a higher gain, and also that the radiation pattern is going to change from the horizontal plane to the vertical plane, meaning that now the DRA is resonating instead of the graphene dipole. So we tried other designs of antennas that could benefit from this reconfigurability, and the next one was a Yagi-Uda antenna with graphene. Basically, here on this picture, we have 4 Yagi-Uda antennas looking up, down, left, and right in this shape. And the idea is that all these elements are graphene, so that we can tune in and tune out these different elements, so that one of these 4 Yagi-Uda antennas would be the one resonating and radiating. So that's why on top right, you see 4 different patterns in 4 different colors, which is when you tune in different of these dipoles and different of these parasitic elements for each of the modes. So you can reconfigure which is the direction at which you're going to transmit at different times. And the picture at the bottom, we demonstrate that you can do that while you are also modifying the frequency of resonance. So if you provide more parasitic elements at different distances, and you select them carefully, you are able to provide this spatial reconfiguration at different frequencies. So you approach joint frequency beam reconfiguration, which is very, very, very hard to provide with metallic antennas alone. Then the next step was try to generalize this idea of having multiple directions and multiple frequency resonances in the form of metasurfaces. You know, metasurfaces are some sort of very dense arrays of antennas, and they are characterized by the units. So we started by trying to design a unit cell which had graphene on top of a substrate and having a metallic backplane, and playing with the different dimensions and the different dimensions from the of the graphene patch, from the graphene patch to the edge of the unit cell, and so on and so forth, and then changing the chemical potential of the graphene sheet. We could observe that there's this map in terms of amplitude of the reflection coefficient and the phase of the reflection coefficient. And for metasurfaces, it's very important to have a high amplitude and phases going from 0 to at least 180 or to 270. So we picked some points in terms of chemical potential that provide those phases with high amplitude, and with that we started building metasurface for different applications that could be built out of these unit cells. And this example here is for terahertz beam steering, a metasurface reflect array with graphene unit cells, in which if you are able to bias these graphene elements independently, then you are able to encode it in a way that the reflected beam is going to go to different directions, and the plots on the bottom of this picture are going to show different directions. We show that the beam, the waist of the beam is less than 10 degrees, and the error of where we're gonna steer the beam is less than 10%. So with 100 unit cells per axis, which is not more than a millimeter per dimension. We then also applied this idea of a metasurface, a reconfigurable metasurface with graphene unit cells to terahertz near-field communication. So essentially, the states that we apply to the metasurface are changing, and the idea is to focus energy to very specific points in space, in the near-field space of the metasurface, if we want to transmit a given symbol, which is a 1, and then removing that energy from that spot if we want to transmit a 0. So if we alternate these 1 and 0 states, we can transmit energy and transmit information by the presence or absence of energy at that point in time. And we demonstrated that we can also apply different coding of the metasurface to provide this communication at different points at the same time. So you provide multiple streams of information from a single point to multiple points by means of these Terahertz communication. So this is kind of the cornerstone of Whiplash project, in which we are proposing exactly this: graphene antennas for wireless communication systems at the chip scale, and where we are trying to replicate simulation works that try to design an experimental testbed to try to test those antennas. And we're trying to figure out if the antennas actually radiate, and we have the miniaturization of tunability that were promised. And we also are simulating computer architectures that leverage the benefits of wireless communication to speed up the architecture. And in this particular case that I will not go into detail, by just having a wireless bandwidth of 64 gigabits per second in a single channel and a broadcast kind of environment, we achieve up to 4.4x speedups in this particular architecture, which is a lot for computer architecture. More than 4x speedups is a lot, and consuming overall the whole system 38% less of energy, thanks to this wireless communication. So from graphene to the antennas to blending the whole system, we see a significant improvement in speed and energy. So from here, we envisage that there's a lot of work to do in this area. So there are opening questions that we need to research, like how to encapsulate graphene to achieve the necessary carrier mobility to create a resonant antenna, which is generally quite high. What is the actual miniaturization and tunability that we can achieve in an integrated environment? When we have the contacts, when everything is encapsulated, and so on and so forth. And when we go to the lower part of the terahertz band, which is the one that we envisage to use, how can we achieve practical dynamic and local biasing to achieve these metasurfaces that or these reconfigurable antennas that need to bias individually the different elements? How to engineer the metal graphene contacts so to reduce the resistivity, and this way being able to actually introduce the signal into the antenna? How to co-integrate the antennas with circuits that might be in other technologies such as silicon germanium, and so on and so forth. So these are questions that need to be solved to take this theory or these simulations into a real system. But in conclusion, modern computing systems call for very versatile solutions at the interconnect level, solutions that wireless technology can try to respond to with their low latency, system level flexibility, and inherent correctness capabilities. But it's with graphene antennas and its many challenges, though, that we can achieve the actual benefits of this wireless technology in a way that actually makes sense, and reaching at least 10x improvement at the system level, which is a significant breakthrough in modern computing systems. This has been funded by the Whiplash project, so if you want more details, feel free to please check out our website. And this reaches the end of my presentation. Thank you very much, and now I'm open for questions.